And I would like to introduce to you Dr. Zhongjie Yu. He is an assistant professor in the Department of Natural Resources and Environmental Sciences here at the University of Illinois. He received his PhD in biogeochemistry from the University of Pittsburgh in 2018. His current research aims to resolve the complex dynamics of nitrogen cycling in agricultural watersheds and production systems, with a particular emphasis on understanding the mechanisms that govern the sources, transport, and transformations of nitrate and nitrous oxide. Dr. Yu.
Thank you so much, Julie, for the introduction. My name is Zhongjie Yu. Again, I am a biogeochemist by training, but since I started pretty much 3.5 years ago here at UIUC, I have been trying to educate myself a little bit and trying to be a biogeochemist who also knows some agronomy. So today I'm gonna present some, how does this work? So yeah, some results from our projects conducted at both field scale and also watershed scale. So what I show here, basically on the top kind of panel, is a long-term 30 years record of weekly nitrate measured in the upper Embar River watershed. So I put a little bit, a little map on the upper right. Just this watershed is not too far from here. And this long-term record was started by Mark David and Lowell Gentry, and we continue to sample the river for nitrogen and the phosphorus. So one thing clear from this figure is the nitrate load didn't seem to change much over the 30-year kind of time span. Nitrogen and water come and goes every year, pretty much year after year. If you look at the lower bottom, that's a kind of close-up look just on 2 years of nitrate concentration data. So you can see pretty much every time kind of during the summer period, nitrate concentration was really low, very close to zero, and also pretty much after the harvest period, concentration started to increase and usually peaked at the period during spring, like May or June, and then it just come back down to kind of somehow close this seasonal cycle. So as a biogeochemist, the first thing I did with this data set just to calculate some watershed budget nitrogen terms and try to compare different terms to see how the input is balanced by the output. So the first thing I started is to look at soil nitrogen. We know we have a lot of nitrogen stored in the soil. So what I show here is results from a previous research by Mark David. So the organic nitrogen compound in the soil, pretty much down to 3/4, can be on the order of 14 or 15,000 pounds nitrogen per acre. There's just a lot of nitrogen out there. And that nitrogen can be mineralized to produce inorganic nitrogen like ammonia and nitrate. And this nitrogen can return to the organic nitrogen pool through this immobilization process. Then we have this nitrate leaching, which was based directly on our weekly nitrate sampling at the Embar River. So it's about 22 pounds nitrogen per acre. If you look at the picture on the lower right, that shows the annual load we calculated over this 30 years time span. So the next thing is input through fertilizer, nitrogen fertilizer. We had 81 pounds nitrogen per acre. So this rate was much lower than the typical rate to corn, but this is a watershed average value. So we account for the soybean acres, which was not fertilized, and also it pretty much has the same acres in our study system. So we got, again, 81 pound nitrogen per acre. And if you look at the figure, that's the temporal variation over time. One thing very interesting to me is the fertilizer input increased pretty much after 2019. So I still don't know the cause of this increase. If you have any idea about this, just please let me know. And next input is soybean biological nitrogen fixation. We got another 80 pounds nitrogen per acre, which was estimated based on soybean yield every year. Then we have output through nitrogen harvest in those corn and soybean grains. We have 125 pounds nitrogen per acre. And this value has been increasing over time due to the increasing yield in this watershed. So based on these calculations, we can define this term called nitrogen surplus, which basically is fertilizer input plus soybean biological fixation input minus the nitrogen output through grants, and plus some small terms like nitrogen dissolved in rainwater and also manure applications. So we have arrived at this number, 47 pounds nitrogen per acre. So you can see compared to our leaching loss, this is a larger number, right? So that means the nitrogen budget for this system is not closed. But one thing I want to point out here is these numbers are not without uncertainty, but that just reflect our best knowledge at this point. Actually, we revised this multiple times. My student, Ming Hui, is actually leading this effort. We just updated this value this week in order to make sure that we present the most accurate result to NREC. So another thing I want to point out is you may think those numbers, input and output, are small values compared to organic nitrogen in the soil. But one thing is, based on previous research, that not all those soil organic nitrogen are mineralizable, meaning that they're not all of them are biologically available. So actually any change in those input and output terms can't matter, especially you kind of integrate over long-term period, like 30 years and 50 years. So one thing missing from this balance is denitrification, which is a microbial process which reduces nitrate to produce those gaseous species like nitrogen and nitrous oxide. This process is super challenging to quantify. There is almost no way to directly measure denitrification in any system. But knowing the magnitude of denitrification is actually important, because if this flux is remove nitrogen at a high rate, the total nitrogen output could be, which is the sum of leaching and denitrification, could be larger than the nitrogen surplus, meaning that we have a net depletion of organic nitrogen from our system. But if we have low denitrification, then we have a net accumulation of nitrogen in the soil. So with these kind of initial observations and thoughts, we developed 3 overarching research questions. One is just, where does the surplus nitrogen go? Are we gaining or losing soil nitrogen over time? The second is, what sources contribute to nitrogen leaching to the streams, to the rivers? Is it soil nitrogen or fertilizer nitrogen? So actually, since I started my job here, I got asked this question by numerous times by my colleagues, by Lowell, by the head of my department, by the dean of our college. It seems like everybody is interested in knowing the answer for this second one. But actually, to me, it's not that important. Nitrogen is nitrogen, right? And also, a lot of times you cannot really differentiate between these two sources. As soon as you put the fertilizer on the soil, a lot of them can be assimilated, become part of soil nitrogen. But I think an answer to this second question could help us to better understand the first one: where does the surplus nitrogen go? And the third question, I think, is the most important one here. Is it possible to reduce nitrate loss while increasing soil nitrogen and crop yields? Now we just heard from Lo that it's possible at the field scale. We can better manage the field, reduce the nitrate load from tail drainage. But I would like to ask, is it possible at the watershed scale? How can we translate or extrapolate the knowledge we gain from the field scale to complex watershed systems where soil and management could be highly heterogeneous, and also weather hydrology can be a lot more complex? So I think the answer to this last question is still not that clear, especially at the larger scale. So to solve these questions, we use stable isotopes. So for those who are not that familiar with isotopes, basically they are the same elements of the variants of the same elements. So in our case, we measure the nitrogen isotopes and oxygen isotopes in nitrate. So we usually using a plot like this, shown on the lower right, to kind of study the source of nitrate. The idea is different source has different isotopic ratios, those ratio of heavier to lighter isotopes. And that can be used, we call that fingerprint, to understand different sources and their dynamics. So again, in the following slide, you will see a plot like this a lot. So for the horizontal axis, that's the nitrogen isotopes. So it goes from negative values to positive values. Negative values just means your sample nitrate has a less heavier isotope compared to nitrogen in the atmosphere, which is the ultimate standard for all the isotope measurement. But you have positive number that's more heavier nitrogen is in your sample. So you can see on that figure, different sources kind of occupy different regions. That's how we can kind of differentiate these sources and their dynamics. Another thing I want to point out here is you see this kind of straight line, right, on this figure, which we call denitrification line. Every time denitrification happens, it actually can shift those samples to upper right. So that means in order to review the source signature for your nitrate, you do need to account for this denitrification process. So here's some data we collected from the replicated site. The site just Lowell just introduced. So we have 3 years of data for tile drainage nitrate and also nitrate isotopes. So if you look at this, we have corn, soybean, and corn. One thing I want to point out here is, again, the top one is for concentration, the lower one is for nitrogen isotopes. You can find that they almost follow kind of similar patterns, kind of mirror the pattern, but in a reverse fashion. So every time you have a high nitrate concentration, for example, after fertilization during this corn phase, we have really low nitrogen isotope ratios. Another thing interesting to me is if you focus on the soybean, which has really high concentration, almost 8 milligram nitrogen per liter, kind of stable over time. And also this soybean year has a higher nitrogen load compared to this, the second corn yield. So you may wonder, what could be the source for this nitrate in the tile drainage? So here is a plot. We basically show these measured isotopes in this we called fingerprint plot. Again, nitrogen isotopes versus oxygen isotopes. So on this figure, basically, if you look at this lower portion, the horizontal zone, that's when the zone for nitrification. So when the nitrate is produced from those different sources, they're supposed to basically lie in this horizontal region. So we did actually lab experiment to characterize this range, and actually my student in Chawell have a poster about this process. If you want to learn more about how we design and also quantify the nitrification signal, please stop by her poster. So again, you see all the sample kind of fall above this nitrification line. That means all these samples went through some denitrification. But after you kind of take those back to this so-called source zone, and they all fall within this shaded gray area. Okay, so I'm not sure if you can see that clearly, but then you can compare that original source to different kind of isotopic end member. What I have here is the nitrogen, the anhydrous ammonia, soybean biomass, soil total nitrogen, and also the corn residues. So what we found here is after the correction for denitrification, all the sample have similar isotopic signature as fertilizer and soybean biomass. But there is one important caveat I want to communicate very clearly is that we cannot really differentiate between fertilizer and the soybean because they have almost identical isotopic ratios. The reason is simple because they both derived from nitrogen from the atmosphere, right? The soybean through the biological fixation, the fertilizer nitrogen is through the industrial fertilization fixation process. So we did the same thing for the river nitrate. Here what I show is a 3 year of isotope data measured at the Emba River. So kind of the same pattern you see as the last slide. We always see this kind of mirrored but reverse kind of pattern. When the nitrate concentration is high, the isotope value was really low, and then when you have declining of nitrate, the isotopes start to increase. So here, the same fingerprint plot, but in this case for river nitrate. Here I use different size to show nitrate concentration. Pretty much we get the same result. After you account for the denitrification impact, all these nitrates show isotopic signature, which is very similar to fertilizer and soybean. So with this result, we kind of took a step further, right, do some modeling work to really answer our first question: where does those surplus nitrogen go, and how they kind of partitioned into this watershed system. So here is our model. We have two components, one for surface soil, the other for groundwater aquifers. So the first thing we did is we kind of split the total soil organic nitrogen into two different pools. One we call active soil nitrogen, the other is passive nitrogen, to kind of somehow account for the different reactivity of organic nitrogen in this big organic nitrogen pool. And then these active and passive nitrogen can be mineralized to produce nitrate, which can be leached to the groundwater component and also can be denitrified. So you see every year we pretty much split that surplus nitrogen into active nitrogen pool, passive nitrogen pool, and also directly to the inorganic nitrate pool in the surface soil. So for the groundwater component, we use hydrological tracer chloride to basically quantify how fast water is moving through this groundwater system. And also doing this traveling during the groundwater, nitrate can be further denitrified. So you see there is a second denitrification term right here. So we calibrate this model to our both weekly measure the nitrate concentration, and also we incorporate those isotope effects into the model, so the model can also basically simulate delta N15, that's the nitrate isotopes, just to better quantify all these unknown variables. Here is some kind of simulation results from the model, and the model can achieve really good simulation for annual load. So on the top one, I show this observed versus modeled annual nitrate load in Amba River. We can achieve R squared almost 0.8. In the lower one, there's a model and observation comparison for flow-weighted mean concentration. The performance is not as good as load, but still acceptable, in my opinion, R squared about 0.4. So here's the results kind of from that nitrogen balance simulation. So here I put one basically number for each kind of process, and also you have a plus and minus to account for the model uncertainties, right? Model is not perfect, there is always error associated with it. So remember we have that 48 pounds nitrogen per acre as a surplus kind of over this 30 years. Our model found that about 33 pounds nitrogen per acre went through this active soil organic nitrogen pool. A lot of those kind of surplus and then get mineralized from this active organic pool to become inorganic nitrate in this case. But there is also input to this passive organic nitrogen pool and also directly to inorganic nitrate in the surface soil. For this surface nitrate, 2/3 basically leached into groundwater and about 1/3 get denitrified. So during the traveling of this nitrate through the groundwater system, there's another 9 pounds nitrogen per acre get denitrified, which gave us this 22 pounds nitrogen per acre as the river export that we measured over the 30 years. So here again, from the model simulation, that's the variation of different nitrogen pools over time, over this 30-year time span. The first one for passive nitrogen, the second one on the top for active nitrogen, the lower two are for inorganic nitrogen, nitrate in the surface soil and also nitrate in groundwater. The key take-home message here is the passive organic nitrogen almost didn't change much during the 30-year span. So you see here, each dot gives us average value, but we also have an error bar to account for the model uncertainty. But for the active SON, it depleted a little bit. So compared to the beginning and the end of this 30-year, we found about negative 68 pounds nitrogen per acre less at the end of this 30-year time period. But if you look at the most recent several years, pretty much after the 2019, the model found increase of that active soil organic nitrogen. Remember, fertilizer rate increased a lot during this time period. So that directly showed in our model and also caused this increase of active soil organic nitrogen, active organic nitrogen in the soil. But if you combine passive and active soil nitrogen, the total soil organic nitrogen didn't change over this 30-year span. So I just want to summarize a little bit. For our first question, we found about 70% of the surplus nitrogen went through the active soil organic nitrogen pool, which is subsequently mineralized, leached, and denitrified. But overall, over this 30-year time span, the total soil organic nitrogen didn't change. Our second question, we found fertilizer and the soybean residue was probably the major source of nitrate in the tile drainage and also in the river water. However, we cannot separate these two or differentiate between these two sources based on our isotope measurement. So I think I just want to show these two conclusions. We actually have high confidence on these two conclusions because they are based on long-term data sets, isotopic and also concentration measurement. But how you can combine those two pieces of information to generate implications actually depends on how you look at it, right? Different people may have different take from these conclusions. So to me, I think, fertilizer and soybean can be maybe the major source to those loss, but they can also be the major source to our soil fertility. So we just heard from Dr. Below this morning that for the total nitrogen in corn, less than half is from actually fertilizer from the current year, right? Then you may ask, what's the rest of nitrogen coming from? It may come from soil mineralization. But I will further ask, where is that nitrogen comes from? So based on our results, I found that nitrogen could be found past the fertilization to our soil or the incorporation of soybean nitrogen into the soil. That means we probably almost need to fertilize at this high rate and also incorporate soybean biomass at this high rate in order to keep this high fertility in our product system. This is despite, the yield has been increasing, but the organic nitrogen doesn't change. I believe that has a lot to do with the high fertilization input to our system. So that leads to the last question. Is it possible to reduce nitrate loss while increasing soil nitrogen and crop yields? We know now the nitrogen didn't change, like organic nitrogen stock didn't change for our system, and the crop yield have been increasing. But can we really reduce nitrate loss? So I don't have an answer to that question yet, but we have a proposal, we have a vision. So within this upper Ambros River, we have been measuring nitrate load from a small headwater watershed called Black Slough, which is shown on the second kind of figure right there. So we have more than 20 years of concentration data from this small watershed and also from the larger watershed. We found almost a perfect one-to-one relationship between these two watersheds. And then we propose to take Black Slough as our test bed to do experiment to study different management practices and their impact on nutrient loss reduction at the watershed scale. So the unique point here is any reduction at the watershed scale can be directly verified by simultaneously measure nitrate concentration between these two locations, the small watersheds and the bigger watersheds. This can be done using the equation at the bottom. So this is not going to be a direct comparison between two sites, but the fact is the Black Slough is actually nested within the larger watershed. We do need to account for the nesting feature and account for any reduction at the black slough will also kind of slightly reduce the total load of nitrate measured at the larger watershed. So we have kind of set up the both sides. So what I show here is our continuous measurement of nitrate and also flow at those two locations. The upper one is from BLS, the Black Slough, the small watershed. The bottom one is for the larger watershed, the upper Anbar River. So on both of these two figures, the black line is the 15-minute nitrate data, and the shaded area give us discharge for the stream and also for the river. So this is just from last 2 months, from basically the end December to pretty much right now. So we know in this region we had several big events in January, right? So if you look at those two figures, first thing, they're almost identical in terms of the nitrate concentration. That tells a lot about these, these two nested watersheds had almost identical kind of farming practices. And also if you focus on the first 3 pretty much events, stream events, or flow events, every time you have a high flow, you also have a corresponding peak for nitrate concentration, right? And then when we get to kind of the mid-January, we have freezing temperature in this region. The river gets frozen, but following this freezing temperature, we had melting of the ice and the snow. That gave us this last event, a really big event. But we believe that event triggered a lot of overland flow, which actually caused the dilution of nitrate at both locations, the Black Slough and the Anbar River. So I just want to show it there, just give you a sense what we can learn from all those interactions about biogeochemistry, soil management, and also hydrology, right? Just from those co-located, paired, continuous measurements. So we also have daily kind of measurements for water isotopes. So I don't really have time to tell you about water isotopes, but it's basically a fingerprint of water. In this case, it tells us where water comes from. So this is our daily water isotope record measured at Camargo, the bigger watershed. So we can use it to tease apart, okay, this is from tile drainage, this is snow melt, this is groundwater. And also we have this measurement at Black Slough as well. This is how we can extrapolate any reduction we saw in Black Slough to the larger watershed. At the same time, we account for all different hydrology, weather impacts, stuff like that. So this is my last slide. Our focus has been nitrogen for the past a few years, but we just started to do phosphorus as well. So what I show here is that event-based sampling for nitrate and the DRP, dissolved reactive phosphorus, in tile drainage. So this is for event scale. So for these 3 panels, on the far left, we have water isotopes that tell us where water comes from. The middle one gives us nitrate, and the right one gives us DRP. This is just for one event. If you look at the back, that shows how discharge change over time. Again, this is for tile drainage. I want to draw your attention to the right one. So when you see, basically when the discharge starts to increase, the DRP increased significantly. Actually, this pulse accounts for more than 80% of the total DRP load during this event. So this occurred within 10 hours. So this kind of hard moment of nutrient loss can be easily missed if you use daily sampling, weekly sampling. But we started to do those event-based sampling to better understand, those hotspot, hard moment kind of behavior. And also my student, Carlos, is the one leading this effort. Literally, he goes out every time when it starts to rain, and we start to do this at the Black Slough as well to see how this kind of pulsed release actually translates from the tile drainage scale to the watershed scale. So with that, I would like to thank NREC for the support. I think NREC really should take up the entire page here, but I also want to give credit to Lo for providing a lot of data Dan Schaefer and Eric Miller, without their help, we cannot do any research. And also, the members from my research group, they're really the ones doing all the heavy liftings here. So with that, thank you, everybody. Happy to take any questions you may have.